So just to recapitulate, we defined red-black tree, RB tree as a binary search tree with these 4 axioms. Right? So it's a BST. Every node is red or black. Red can have only black children, and on every path from root to leaf, black height is the same, which is the number of black nodes. Then we have this quick observation. First quick observation was this second statement, which is the black height can be at most height plus 1. So this I have corrected so height as we have defined in the class is the length of the path from root to leaf. And black height we have defined as number of nodes, black nodes. So black nodes can be at most height plus 1. And they will always be at least height upon 2. Okay, so if you have height 3, then it means there are 4 nodes. So out of 4, minimum have to be, well, so out of 4, so if you have 4 nodes, then you should have black at least 2, right? Because red and black, they have to alternate. So lower bound is simply height upon 2. That is fine. And then we prove this main property. The lemma is that the height, just because of the 4 axioms, is always logarithmic in the size of the tree, which is the number of nodes. Okay, this does not mean that it's a balanced BST, but still it gives us what we want. So there were some issues in the proof. Basically, you have to be more careful about the case of even height and odd height. So that I have corrected. I will post it after the class. The idea was again to get this recurrence. You write MH, which is the smallest tree of height h. In fact, in the proof I will call h to be the length of the with longest path having h nodes. So h here will be the number of nodes on the longest path. So we oriented the longest path on the left side. It has h nodes. And then we said, we deduced that on the right side you should have a black subtree, which is complete. So because of that we got this recurrence MH equal to left plus root plus right sizes. So that is MH minus 1 plus 1 plus exponential in h. Okay, so you get height log in the size. So you can see these details later. So let's now move to the important part, which is what does it mean for insertion deletion. So insertion here we will show mainly by examples, and we will not cover all the cases because the cases can be paired up by symmetry. Okay, so if we show some insertion on the left side, the same algorithm can be written for the right side by symmetry. So modulo the symmetry, we will give you all the cases. So first idea is that we will assign a new node red color. So red, remember, we denote by circle and black by square by default. Okay, so when you want to insert a new node, you have to search for its location and create a red node, insert it there. But then the problem will be that either, well, when you insert a red node, can the black height change? The black height will not change, right? So it will remain, the black height as an axiom will remain correct, but still there is one problem which may happen, that red may be a child of red. Okay, so then you have to recolor, but when you recolor, then the black height will change. So then you have to rotate to modify the height. Okay, so the game will be to basically either solve the color imbalance or solve the black height imbalance. Okay, so for those you have these two tools, recoloring or rotating. So let us see this in action. and there will be, and this will very soon become quite confusing for you the first time. So because the cases are, the boundary conditions here are too many. So let's look at this tree. Okay, so this is tree T. T points to the root, which is 46, which is black color, and then we have a 67 in black, then 49 and 83 in red, and let's say that they have these 4 children which are black null pointers. Okay, these are the null leaves, and then there is a subtree on the left side, which I am not specifying. So let's just call it something. So what is the black height of this tree? Yeah, so looking at the right side, it's complete. You can see that you have full information. So you can see that black height is 3, and that has to be preserved in subtree 1 also, whatever it is. It's not important in this example. And what we want to do is insert 83. In this tree. So 83 will be a red node, it will be created, and then you have to, what happened? Already messed up, I think. No, I should not have said this here. Yeah, this is still black height 3, and in this, if you want to insert 83, then it will be the same thing which I showed you before, right? After insertion, so 83 will be created as a red node. Then do a search, and then change the pointers to insert. So when you do that, then on the right side of 67, you can just insert this 83, because as you already saw prematurely, that it will be fine, it will still be a red-black tree. Right? So let's redraw that on the new page. So we have inserted it here. Okay, and this left side we are not specifying, it's not needed. So this 83 is the new part that we have added, and this is still a red-black tree. Okay, now comes a more interesting example. So this was, let's say, example 1. Second example is, now in this tree you want to add 54. Okay, so 54 is more than the root, so you move to the right side. Then it is less than 67, so you have to move to the left. So you go to 67, then you go to 49, and then what? So then you want to go to the right of 49. Right, so you insert here 54 and then what happens? Is this arbitrary? Because 49 was already red and you have inserted a red child on the right, right? So black height is fine. So you will be, basically you will be removing this. So black height continues to be 3, but it is still no good because the 49 and 54 are two reds which are consecutive. So that has to be corrected. Okay, so this requires a color balancing technique. So you have a color imbalance. So we have to do a correction for this. So this is our first correction. So what do you do now? So we can make 49 black. Will it be fine? If we make 49 black, then the black height will become 4 in that path. So then the black height, there will be a height imbalance, black height imbalance at least. So then you have to, then we can try making 67 red, right? So that will resolve the, on this path at least it will resolve the height imbalance, but then it will introduce a height imbalance on the 83 side, right? So you make 83 black, then everything will be fine. Okay, so these are the steps. So the resolution is make 49 black, which is square, then make 67 red, now when you make 67 red, there are actually two problems. One is that red has now a red child, so there is a color imbalance and there is a height imbalance on the 83 side. Both of them can be solved simultaneously by making 83 black. So let's draw the new, so the resulting tree now is (67) is and 49 is 54 as red. And something here. Okay, so 49 is made black, its parent is made red, and its right child is made black. So now again we have black heights all equal. In fact, it's the same as in the old original tree, which is 3. And you can see that red has only black children. And we have added 54, inserted 54, yes? Sorry? More than one way to insert and rebalance. No, so you will no, the pseudocode that we will describe in the class will be fixed. There will be no option left. They will not leave it to any option. So I mean, as we see more examples, at some point it will be clear that we are not, there is no choice. So the pseudocode will make deterministic choices, it will be fixed. So here what we are doing is, as we said, new node is red, so you just insert that after search, and then when you see that the parent is red, then you make the, so parent is red means that the grandparent is black. Okay, it's not a choice, it is already given by the axiom. So it will be like this, 67 black and 49 red. So you swap the colors. Okay, so in the pseudocode you have to swap it. Now when you swap the color, you will see that now red 67 may have red child 83. So there also you have a black height imbalance, so it's better to just make that child black. Okay, so there is no choice. This is basically a case that we have solved. So the case we have solved is, well, 80, so 54's parent, so if you call 54 P, then 49 is the parent of P, 67 is the grandparent, and 83 is the uncle of P, right? So the case when parent and uncle both are red, when they are red, which means circle, in that case you will use this trick, this resolution. What if the parent of P is black? That is square. I think this we did before, right? So when we inserted 83, that was the easy case. So if the parent of P is black, then inserting red is fine. Okay, you can insert that, there is no color imbalance and there is no height imbalance. So this second case was the easy case, and the first case is what we just did on this slide. So these are the two cases we have solved systematically. Is this fine? So this will be a small fragment of your pseudocode for insertion. Okay, just think of, as we are doing these cases, just think of the pseudocode in parallel. So in the pseudocode you will first check whether the parent of P is black, and then you can simply insert whatever you wanted to insert, no resolution required. Or the parent may be red, and then you check what is the color of the uncle. If the uncle is red, then you use this slide. And next you check a case where parent is red and the uncle is black. See, now in this class you only ask me questions about what is written on the board. If you ask other questions, it will be hard to verify. I see. Oh, in this already you, sorry? Yeah, so what is the sequence of conclusions here? Since 49 is red, since this is red, right, it is implied that its parent is black, but 46 could have been red. So what happens in that case? No, no, it's not a root node. Say it is happening locally. So 46 is pointed by something else. It's just a local situation. Because I want to look at only this case that parent of P and uncle are both red. And I want to claim that there you have this fragment of the pseudocode. Yeah, so perhaps what I have to say is that this may recurs back, this may recurs upwards. So when you make 67 red and there is a conflict with its parent, then the color imbalance is now shifted upwards. Okay, so color imbalance will keep shifting upwards and your pseudocode has to now look upwards and see whether that can be corrected with the pseudocode. So this, if 46 is red, so this may propagate upwards. Okay, so we will, so as long as the height, so we want an insertion algorithm which is order height, right? So if our solution is propagating upwards, it's fine. So we can assume now without loss of generality that 46 is the root. Okay, so this is the base case of this fragment of the insertion pseudocode. So now when 46 is the root and it is red, what do? Yeah, then you use the solution suggested that, well, it is this example, 46 is the root and 46 is red, so you can make it black. So we assuming that 46 is black is fine. Yeah, so those things are kind of inbuilt in our examples, in our pseudocode fragment. Okay. So what next? So the remaining, actually main case is now, which will take more time. It is that parent is red and uncle is black. So red is a circle and uncle of P is black, which is a square. So yeah, again in this picture, let's overuse it. So uncle of P, which was 54, right? That is 83. So if 83 is black and 49 is red, you can again deduce that 67 must be black, right? Because if 67 was red, then 49 cannot be a child. 49 is red. So this also means that grandparent of P is black. So now let us get out of this example and look at it a bit more abstractly instead of numbers. So let me draw a more abstract picture for this fragment of the pseudocode. So you have G you have D, you have K, then you have parent, sorry, not parent. Let me first draw this. Okay, so this is what has been newly introduced. Okay, this is what has been inserted. You did insert P, and so this is insert P operation. This is where the imbalance is. So the imbalance is here because you just inserted P here blindly without correcting the parent of D, who is also red. And other cases we have solved, so it means that the grandparent of P is which is G in this case is black, and its right child is also black. Right? So this is the case where we are stuck. And G is pointed by X, so this is just a local situation where we are stuck currently. Is this clear? Here we want to now resolve the imbalance. So you have to write a pseudocode which so okay, let us also look at the black height. So black height has not changed, black height imbalance is not there, which means that from X when you come to leaf in 1, you have some height H, and when you come from X to 2, you have the same height, and when you go to 3, you have the same height, right? So black height is currently not changed. It's only a color imbalance. So what do we do here? So what we will do here, the resolution is, let me just already jump to that. So first thing we will do is we will rotate, right rotate around G. Okay, so around G we will do a rotation. So what will that give? So G will be replaced by what key? By D, right? So I'll draw it, but first let us just guess it. So when you right rotate around G, then D will become D will come in place of G, and G will go down to K. And what will happen to F? Yeah, so here you should recall your BST properties, that when G goes down, its right child is K, its left child is now free, it is not D, so you can make F its left child, and then D's left child is just P. Okay, so let us draw that. So what you get now is, and let us not change the colors, we'll do that later. This is just right rotation. Yes, and when we bring, as we move this, since we want to do minimal change in the pseudocode, minimal pointer changes, whatever is hanging, 1, 2, 3, it will continue to hang in the same way. Okay, we are not changing those pointers, we are only changing the pointers which we have labeled. So, and D's left is P, is red. Now how about this case? Have we made any progress? So this, by the way, is the definition of rotation. Okay, when we say write a pseudocode for rotate, this is what you have to do. You have to change all these pointers. So for example, X pointer now points, instead of G, it points to D, right? And D's left pointer doesn't change, D's right pointer now points to G. So it's all very confusing in terms of pointers. When you look at the pseudocode, it's impossible to understand it unless this structure is given in the comments. Okay, this is a very complicated permutation of pointers. So we maintain this pictorial structure in mind to understand rotation. And so on the right side, has the height, black height changed? No, it has not changed, because, so always remember that when we get red on top, the black height won't change. So in the right side, let's say 3, K and 3, G was already an ancestor, it continues to be ancestor, and D is red. So whatever happens in X part above will not, I mean, still the height is the same. What about P side? P side, G is gone, as G is not an ancestor anymore, so height has reduced. So and anyways, there is a problem of red D having a red P as child, right? So this is all unstable here. So there is an imbalance of both color and height. So let me say imbalances. Okay, so it has both the imbalances. So what was the point of this operation then, if we have increased the imbalances? We can make P black, okay. Will that solve it? Solve all the imbalances? Okay, so let us do that. So if we make P yeah, somehow I don't want that in the pseudocode, so why is that? Instead, what I want to do is, I want to swap the colors of D and G. Will that work as well? Yeah, let me go with that. So we'll swap the colors of yeah, so somehow I want swapping as a basic operation and not just changing a color in an opportunistic way. It won't change what? Above, yeah, but your solution of making P black. Yeah, that's a very good point. K could have been, no. We are in that case. Uncle is black. No, so whatever colors I have given, they are fixed. Again, as I said, there is no option. This is a fixed case. Only discussion is about whether we should make P black. Yes, so that is very important. So this is why we are going with this swapping, because the point is that there could have been an issue in this part also. That also could have been, we could have introduced an imbalance there also, because X was previously pointing to black and now X is pointing to red, which could create a problem above, right? So when you did the right rotation, we actually added imbalances both on P side and on X side, possibly. So to make it, so the only safe way is actually swap the colors of D and G. So right rotation might have added imbalance on X. Rather this arrow, X arrow D, which is now solved. Okay, it's not always the case, but since you want to give only a local solution, you have to cover all possibilities. You should not leave anything unexplored. So since G was black, you wanted X pointing to black, so you make D black, and then to also resolve the height imbalance, you make G red. Okay, so that's the solution. So let's just for confirmation draw the final picture. After insert, just by local operations and very small operations on the pointers, you get this. Okay, so let's compare these two. Yeah, so D is black, G is red, Fk are black with their subtrees 2 and 3 respectively, and P is red with its 1. So now all the imbalances are gone in this. Okay, and we have inserted. Goal was to insert P and resolve all the imbalances. So this is now balanced. This is now arbitrary. Is this fine? Yes. Yeah, that's dangerous. You'll find some mistakes. Okay. Well, we have to do what you ask. Original tree. Are you looking at the number case or abstract case? The number 46, 67, etc. Yeah, this one. No. So this is the abstraction here. Is the case where we were stuck, which is parent. So it's written here. Point number 3, remaining case. Parent is red and uncle is black. No. Insertion happened like above. When we inserted 54, insertion happened and we tried the fragments above. They did not work. Before it was an arbitrary. No. This is a stuck case. Here you don't look for arbitrary. No, no. Yeah, but okay, let us look at that. Mm-hmm. Yes, so the thing is, where we have inserted P, there hypothetically there used to be a leaf node which was black, and in P, inside P also there is a leaf node inside 1. So, I mean, again, this is an abstract case, but if you want to if you want to specialize this to numbers, then there was a leaf node before, and now when you inserted P, the leaf node was made red to P, but P has children which are black. So the height, whatever the height was before, continues to be the height, black height. That there is no black height imbalance, and obviously before there was no color imbalance. So it was a red black tree. No, when you removing P means that you are putting a square there with nil. No. See, no. So there is also an X. See, this is not the complete RB tree. We have not drawn the complete RB tree. It is just a patch. You can fill the X part and 1, 2, 3 to make it an RB tree. This is just a local computation we are doing. So if you remove P, well, let's just say that if you remove P, originally you had an RB tree, and now you have inserted P and you are in this situation. So that should be a side note here. I mean, this was how we reached this actually. We came from this example, 54 example, and then we reached this. But in general, the assumption here is without P, we have an RB tree. That is the assumption. Okay, in this part of the pseudocode, this is how we got stuck. There was an RB tree, then we added P, and then, but you should not think about this too literally for insertion, because this is a general pseudocode fragment to resolve color imbalance. Okay, so one can be a big RB tree itself. So don't just think of P as a single thing you have inserted. You might have inserted a whole RB tree here, and we have given an algorithm here to remove the color imbalance. So this is a general pseudocode. It's more abstract, but certainly you can apply it to insertion of just P also. That's fine. Okay. So then we are basically done with insertion. So what we have deduced at this point is that this new tree is an RB tree. And it took only log of the original height. Sorry, took O big O of original height of T time, which by the lemma you know is less than equal to log of the size of that. Okay, so why did it take only height T much time? Because locally we were working with very, very small structures, changing the pointers, so that is constant time. And then if we propagate it, well, anyways, when you searched, you have already spent time height of the tree. So you search, you insert, and then in the color imbalance, if you propagate the problem upwards and go up to the root, so then that again is height T, right? So overall it's order height T time insertion. which you know by the lemma of arbitrary axioms, is only log n. Okay, so this is an insertion algorithm of time log n. Is this clear? Okay, so if you are not convinced that these are the only cases, you have to do some exercise. As I said, the pseudocode fragments will have symmetry. So you will write one pseudocode fragment for left orientation, and then the same thing you can write for the right orientation. So here in this slide, what I have shown you, I am biased towards the left, right? Because I already put P on the left side, left child. But obviously this may not happen in practice. In practice, maybe P appears as a right child. So you have to also handle that case. So you have to write the symmetric left to right pseudocode. Okay, it will be a copy paste and then some edits. Sorry? In the implementation, yeah, so I think all the arrows you can assume them to be like double links. That will help, I guess. That is correct. Yeah, but yeah. So I think in the mathematical modeling of tree, we had said that for a node there is a function parent, and that meant that it should take only constant time to access the parent. Yeah, that's already in the mathematical modeling. So parent, even grandparent, and child, left or right. So for all these, you have functions that immediately give the result. So yeah, for implementation, just assume doubly linked. Yeah, so wherever I am saying left or right, and giving the pseudocode, you have to write the symmetric pseudocode. Right, so here we did with, in the case already we said, we did not say in the case, but at least in the picture, we have already biased towards left. So you have to write also, handle the right side also. So that I will not repeat. So let me just leave that. When P appears on the right side. Okay. It's already, class is over. So what I will do is, whatever we can't finish, I'll post it online today. So the next thing is now deletion. So deletion will be, again, the tools will be, basic tools are the same. You have to handle either color imbalance or height imbalance, black height imbalance in particular, and you will use color swaps or rotations. That's it basically. Yeah, but you rotate or you do color swap. So let us see some examples. So we want to delete P now, which already exists in the tree. So let's take an abstract example again. P is here. It has a black left child, nothing on the right side. subtree and x. I think this one, okay. Yeah, so you want to delete this p. So when p goes away, you are left with the x part, of course, and the q part. So what should happen? Yeah, so we have just this remaining. Is this an arbitrary? It is, right, because it is just the left part essentially. So these are the easy cases when p has only one child. Okay, then you essentially do this. So this is one case. Similar cases when p is color black. So what happens in this case? When you delete p, sorry? Right, yeah, so there is one more operation here, changing the color and get the same thing. And the third example is and you have that subtree hanging. What do you do here? So here what you are left with is black q, one x part pointing to this. Is this an arbitrary? Yeah, so it may not be an arbitrary. Why? Yeah, so what has happened is that this left part of x is uniformly unbalanced in black height. Right, so there is now a uniform imbalance here. So let's denote that by this minus sign. So overall on this side of x, the black height has become -1 for whatever path you take. Right, so for this now we have to look at a bigger structure and repeat those rotations and color swaps to deal with this special imbalance. So it's really not q subtree but of x subtree. So this is the hard case which has 2 or 3 cases, so that I have to now put online so that you can read for the midsem. On Saturday I think there is a tutorial planned. So this tutor should send you an email and they'll also show you you can discuss the quiz and other questions, assignments.